Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to give you more detail about how to design a FMC-based inspection technique and see how BeamTool leveraged point spread function simulation to provide tools that can help us to make sure that the FMC technique we design is efficient for TFM or PCI imaging. In the previous videos, we introduced point spread function simulation, and we explained how BeamTool simulate the point spread function and how it then use that to generate quality maps for FMC technique. If you haven't watched that video, I encourage you to first watch that video to get more familiar with this concept and then come back to this video. But here, assuming that you know the details, I'm just going to give you a quick overview. The point spread function is an image of a small point reflector that you can think about as a tiny sidereal hole. And from that image, we can see a distribution of intensities or amplitudes that the peak can correspond to sensitivity. The size of this blob would represents the focal area, and the vertical and horizontal extent of that can be correlated to vertical and horizontal resolution. Now, here I have a piece, and I chose not to put a weld in it for this example. And when we want to design FMC technique, because FMC also is a technique that is generated by using phase array probe, we come and in our probe section, we choose phase array. As you remember from previous videos, that gives us an option here to choose our probe and wedge. For this example, I want to use a 5L64A12 64 element probe with 0.6 pitch 5 megahertz. And I'm going to use SA12 M55S as a wedge that works with that. Then, the next step would be to go on a beam set and choose full matrix capture. When we choose full matrix capture, now we have a dialog here that gives us all the parameters of that we need to set for our FMC technique. The first step would be to just choose how many elements we want to include our technique. By default, the BeamTool will use all elements, and here in this example, I'm not going to change that, so we're going to use all 64 elements. The next step would be to choose what type of imaging path we want to use or sound path we want to use. We have option to choose different paths on transmit and receive. If I click here, I can choose to have direct shear, direct longitudinal, or shear after skip, or longitudinal after skip. And for this example, on my transmit, I'm going to stay with direct T, and I receive also, I have all those options, so I can mix and match. For this example, I get T, but for instance, if I wanted to choose TT, then I would go to a self-tandem modes of T-TT, but it's in the example, I stick it to RT. The next thing that I need to set would be the actual image domain, where I want to image. What is going to be my location of the image with respect to the probe and wedge. And here, we can specify that as a box from top, bottom, left, and right. Here, I want to extend this to be starting from -25, and here 25. And then start box from 0 to, let's say, matching the thickness that we have, which is 10. Now, in this point, when the box is chosen with respect to our coordinate system in BeamTool and the probe and wedge is located again with the same, now BeamTool would know what is the relative position of the box and the array and the wedge that we're going to use for imaging. The next step then here, we have other parameters here that we can choose in terms of the pixel size, how many pixels we want here, what is the size of they gonna be, and for this purpose, again, I'm gonna choose 0.1 millimeter on both direction, and knowing the size of the box, BeamTool can tell you that how many pixels per one wavelength you have here. Now, the next step here would be, at this point, I chose the box I want to render an image, but next step would be now actually go and try to assess this. And that's where we have the FMC quality tab. And this is where, if you hoggle on, this is where we use the pointer split function simulation and try to get different parameters from that to assess how well an image can be generated in this box that we chose based on this imaging system. You notice that here, if I click, this gives me a list of different options. It's by default on sensitivity. You have pointer split function preview, focal area, horizontal and vertical resolution. For the simulation to run, you click on this icon here, and what happens on the background, all those simulation tasks that we explained in the previous video, I'm gonna go over, and here you can see the sensitivity map. But before that, I want to go first to this pointer split function preview. What the pointer split function preview is, it actually gives you the image of this pointer split function in our imaging domain. As you move my mouse here, you start to see this small indication that essentially is a pointer split function or image of a tiny hole at every location that my mouse is. So for us to look at this a little bit better way, I can zoom in this region, and here you can see that when I am at top, I have this tiny blob, which is basically a 6 dB drop from the max intensity of the image that we would get from a tiny side drill hole. And if you see, if I move it down, you see that the size is pretty consistent, but now you see that the amplitude or intensity of this is much higher. And as I move this, my mouse to the right, pretending that my point reflector is located at the bottom right, you notice that as compared to when I was at the bottom left, both the size of this pointer split function or blob increases, and also the intensity or amplitude decreases. And if I move up to the top right, you basically see that I'm really getting out of focus, and two things happen. First, my blob is much elongated, deviating from what original size of a small hole would be, and also the amplitude drops. And if I keep moving to the left again, as I get closer and closer to my probe and wedge, this size aspect comes back. So the size of the pointer function get closer to what you expect from a small hole, but still the amplitude or intensity is low as compared to when it is at the bottom left. So this gave us a preview of these intensity changes as we move in our images. But to now look at it as a map, we can look into sensitivity. When you look at the sensitivity, what you can see here is a color palette that ranges the minimum and the maximum amplitude or max amplitude of the blobs that we saw before moving in this imaging domain. And they're all now here. And to just give a context, you will see a shadow of the blob that we looked at before, or the pointer split function, on the background. So again, you see that as I move to the bottom left, as we saw before, the intensity of this pointer split function was higher, the amplitude was higher, so we get very high sensitivity value. But when I move up to the top right, what happens is that I get very low sensitivity value, and that's because now the intensity of the image of a hole that you get further away from your active focus become basically smaller, and that's what this map represents. To better understand and correlate this to the common experience we have, I want to load two images of side drill holes that was inspected by FMC TFM. The first image will be basically images of bunch of side drill holes that are all in the same arc, pretty much on the same area that you can see here in InspectionTechnique, and all these holes are on the same order in terms of size. And the image that you can get from them in the TT mode when we do TFM imaging based on FMC technique will look like something like this. I'm going to move this image slightly to the right, so all of them, we can see all of them on the screen, and maybe move them a little bit lower. So now these images can help us to better understand this context. This is the actual side drill holes on the blob and on a block that was imaged with this technique, and this is actually the TFM image that we get. If I zoom in here, now you can correlate point to spread function to these images. Here you notice that when we are at the bottom here, bottom left, both the size of this, the shape of this point inspection is closer to the holes and its intensity or sensitivity is higher. Exactly as you see here, you get much closer to the actual size of these holes and high intensity. But as we move along this arc up to here, then we start to get a blurred indication or blurred, basically elongated arc and low sensitivity value. And that's exactly what you can see here. So this essentially, this tell you that how powerful this point spread function simulation is to actually give you a good sense of what kind of image you can get or how well your imaging technique can work. Now, as we talked about before, obviously there are other tools, also other maps that are available. So we looked at sensitivity. Then we can go to focal area. Focal area is mapping the size of this blob, or like the overall size of this blob in our imaging domain, which basically indicative of how focused we are. And again, you can see that the palette is ranged between basically like a small value to a large value, from light purple to yellow. And as we move our cursor on our mouse on the image, we can see its focal area values. And what is interesting here is that, again, when we are close to the bottom left, our focal area is around 0.33 millimeters square. But as we move up, you see that start to increase to 1.33 or 27 millimeters square. And this range, what it means is, as we go to top right, our focal quality or focal size, essentially like the focus is not as good, so our focal size or the beam size increases, and that means that your in the indication you see in the image will be more blurred as compared to its original size, and that's exactly matching the expectation that we see here. But this is just to give us an idea about how our focus changes. Ideally, we wanted all these area to have a very, very uniform, basically low focal area. And these are the things that when we design a technique, we can play with parameters such as probe frequency, size of the aperture, all these things, so that it can reach to the goal that we have a uniform focal performance in our image domain. Next basically map that we can use here is horizontal resolution. Again, we have basically a color range that gives us a palette, and when we moved, we have a shadow point spread function, but also here you can see that as you move from left to right, what kind of changes you can expect in sizing or relative size of those blob. And again, when we go further and further from our location that we have the best focus, the size of these blobs elongated, so it's both on the horizontal and vertical size. So here, if I come to the vertical, also you can see here the vertical extent here would be lower when we are at the best focus, and it basically get larger as we go higher and higher in the imaging domain that we don't have a perfect focus. So these tools gonna help us to design our technique. Any changes that you want to make to our technique in terms of the sound path mode, location of the box with respect to array, size of array, frequency of array, will be the changes of those things. The effects of those things will be evaluated based on how it changed these quality maps. And based on the goal of the inspection, we choose the parameters that best give us the best map that indicates the best performance for our inspection. And in the next videos, we're going to give you examples of how we use these maps to choose correct parameters for inspection technique, and how we can use these maps to compare between techniques to choose the correct one for our inspection technique. Thank you so much for watching this video.